Okay, so let's get going. Let's use some math in the real world. So I want you to take 5 minutes, look over this graph, read everything about it, write down a few observations, and then after you've had a chance to reflect on it yourself and write down a few thoughts, compare it with some folks at your table, and we'll talk about it in about 5 minutes, 4 or 5 minutes. This, I don't want to get people, we're going to learn about doubling rates, but I'll leave that. I can tend to go beyond, but that's like the last 4 weeks. Yep. Right, so it is not a constant rate of change, is it? So the annual increase is not constant. So it doesn't have a slope that's constant. Okay, what else did you notice? I heard someone talking about this stuff right here. I think it was Beth, about right here what was going on. Were you talking about that, Beth? About the 3,000? What were you saying? Right, right. Right, so notice, see that little, and that's the next thing you see down here. I cut and pasted it down here. This is really interesting. When you pass in a graph to me that doesn't start at 0, you use that little symbol to say there's a break in the axes. This indicates a break in the scale. The axis does not start at 0, basically. Okay. That's really important. So basically, they just kind of took the vertical axis and it's like literally cutting out all of the values from 0 to 3,000 that were not relevant and just scooting it down. Okay, that's what they did. Okay. So that's interesting thing to notice. What else? Yep. Absolutely, right. So 2003 to 2004 shows the largest increase so far, right? Yeah. Now, what if I created some ordered pairs here? And I said, okay, 2000 is my independent variable. And I put a little dot right in the middle of each of these bars. So it was $3,362 in 2000. And then in 2001, it was 3,487. And what if I did a bunch of data like this for all of these points, and I tried to find a mathematical equation or a model where the graph of that model would go through as many of those points as possible? What type of equation do you think would fit that the best? Would go through as many of those as possible. What do you think might be a good representation? Tina? No. Tara? Yes, I knew. T. Right, yeah. A line of best fit. So there probably is some type of straight line, and if I had this with me, instead of this, thank God I came in early yesterday to check this out. So there's probably some type of line that you could put on here that represents this data really well. It's not going to go through all of the data points. It's going to overestimate some and maybe underestimate others. But you might be able to find a linear line that would have a constant rate of change that could be used as a predictor. Can anybody else see perhaps another possibility? Yep. A quadratic equation, right. You might be able to fit, let's see, what do we want? What color? Let's go here. Let's do purple. You might be able to find some type of curve. Whoops, I didn't do a very good job, sorry. I'm not good with the mouse. You might be able to find some type of quadratic that fits that as well. That would be an example of a model. It would be a relationship between the year and the cost that would allow you to estimate or predict. All right. So as a student in public higher education, what questions about the average cost of tuition and fees might you want to ask or know about in the future, perhaps? What might you want to know? Will there be a cap? Right. So will these costs continue to rise? Or will they level off? That's what she means by a cap. That's what Mary meant by a cap, right? Are they going to continue to rise at the same rate? When might you be going to a 4-year school? 1 year, 2 years, 3 years? What's going to be the price and 3 years from now, you know? So those are the kind of questions that models will help you be able to answer. So you can read this on your own. It's the definition of a model, but we're going to see a model right now and work with it. Here's a model right here. It's a formula, it's an equation where T represents, the variable represents the average cost of tuition and fees. And this might be new to some of you. X is going to represent the number of years after 2000. So in other words, even though our graph said 2000, 2001, 2002, when we go to calculate the tuition using this model, we're not going to put in 2000 here or 2006 or 2007. We're just going to basically be taking how many years after 2000. That's what X is going to represent. How many years from 2000. So if I were rewriting those ordered pairs that I did back here, what would this ordered pair look like right here instead of $2,000 and $3,362? What would the new ordered pair look like for that model? What would I write instead of 2000? Not 1, because 1 would be what year? 2001, because 2001 is 1 year after 2000. So what would be the number that would represent the number of years 2000 is from itself? 0, right? So that would be where you would start. That would be 0, 3362. Now, back there, what would this one be? Someone? 1, right, 3,487. And therefore, what would be the value for X for 2010? What would be the value of X? 10, right. Because X is the number of years from 2000. So you put in your variable of interest, 2010, you subtract 2000 from it, and you get 10. So now you're all set to actually calculate what this model is estimating or predicting for the year 2010. We know the actual data value, don't we? If we go back to our table, what is the actual average cost of tuition and fees for 2010? We know the real data. What is it? What's the answer? 7,020, right. So we know the real answer. This is a predicted value. So let's see what this model predicts. 4 times 10 squared plus 341 times 10 plus 3,194. So that's going to be 4 times 100 plus 3,410 plus 3,194. So T equals 400 plus, let's see, what's that? 3604, is that right? No, 66. That's what I meant to write. I was looking ahead. 6604. So that's going to give us $7,004. Okay. So our model is giving us this point. 10 years after 2000, this is what we think. So these are our predicted values based on our model. And the real data says that 10 years after 2000, it's 7,020. So is our model an underestimate of the real data or an overestimate? Under, because $7,004 underestimates by $16. Okay. All right, so let's just do one of these at your seats. Would you, at your seats, just figure out what the average cost of tuition and fees will be based on this model for the year 2050, and then check it with someone at your table to make sure you didn't make any little errors in your calculations. So see what the cost of tuition seem plausible. Yeah, I guess so. It doesn't, I mean, so right now people are paying on the average for 4 years $7,020. It's going to go up to 30 for 1 year. Yeah, okay, it's plausible. Sometimes what happens though is that these models increase so rapidly that the numbers don't make sense. Some students said, oh, I hope that's not true, or that seems way too high. So sometimes your models will, if you go too far outside of your data, your real data set, you have what we call model breakdown. The model is no longer really useful. So for the most part, you got to be careful when you create a model. You want to try to stay within sort of the parameters of your data set, not go too far outside on either end, unless you have really intimate knowledge about the field. Then you might feel a little more confident about going outside. But at this rate, I wouldn't want to make any prediction about the tuition in the year 2050, because as Mary said, she hopes it starts to slow down or starts to level off a little bit. So it's quite conceivable I won't be here in 2050. Let's see, how many years is that? 37 years? I probably won't even be alive. But, you know, I hope I'm not. Anyway, you know, so I won't know how to test whether this model was accurate or not. Yep. No. Yeah. Oh, yeah. This, in fact, if we had side by side right here a bar graph of for the average tuition and cost for private schools, what would it look like? Oh, bigger in what way? Fatter? Taller, right. A lot taller, okay? And the average increase of private four-year schools is 6% every year. So just to give you an example, I whip through this a little fast because it's already 11:30. We're a set. A set is just a collection of objects, okay? One of the ways you can actually represent each of the different elements in a set is the roster method. It's not rooster, it's roster, okay? Some people call it rooster. It's roster, all right? Roster method, where you list the names. And to indicate a set, you have to use these sort of like curly braces. They look like a little profile. See, there's your nose and your eyes, whatever. All right, can't get you guys going. All right, here you go. Let B represent the set of 7 dwarfs. So at your seats, I want you to list the 7 dwarfs. First table to come up gets an extra point on their quiz. Go. What do we think? Am I saying that the absolute value can be negative by this definition? Yes? No? What's going on? You're saying yes? No? Uh-oh. Controversy. What does this mean here? This, yep, Kyle? If X is, how do you know that X is already negative? Right here, this statement is telling you that this definition is based on 2 different parts of the number line. If you take the number line from 0 out to infinity, that's all of your positive real numbers. They belong to this set. And if you pluck a number off of this set and put it in there, you come out looking identical to how you go in. That's what it says. I come out looking exactly the same as I go in. Kyle says, if you pluck a number less than 0, which makes you what kind of number? Negative real number. And X is a negative number. How do you come out, Kyle, according to this? Yeah, right, because multiplied by -1 takes its opposite. So this represents what kind of number right here? What does dash X represent? Opposite of what kind of number? Opposite of what kind of number? What kind of number is X? Negative. What's the opposite of a negative number? Positive. This is the absolute value of X. It's positive because the X that went in was a negative number. So when it came out, it didn't look exactly the same. It did a turnaround. It became positive. Okay? This is what you're going to learn later on to be called a piecewise function. We define this graph right here. This is the graph of the absolute value of X. You can put this in your calculator, and this is the graph you get. Notice all the numbers you put into your calculator, all the numbers for X can be any number, but everything that comes out of the absolute value is above 0 or above. It's non-negative. So that's what that graph tells you. This is the graph of the absolute value. Absolute value can never be negative. Okay. So now at your seats, I'm going to check these before you go. We're not going to get to the group exercise. I want you to write sometimes, always, or never. Read the instructions. I'm going to check it. I'll give you a little check off, and you can be on your way, and I'll see you Friday in this class.